As we saw last time, not all rings have a cancellation property, meaning that if I have AB equals AC, where A, B, and C are elements of an arbitrary ring, I can't necessarily conclude that B equals C. Sometimes that will be true, that we can make that implication, sometimes we can't. And we saw the following example from last time. If we let R be the ring Z mod 12Z with operations of addition and multiplication modulo 12, then we have that 3 bar times 7 bar is equal to 9 bar in this ring, but that's also equal to 3 bar times 3 bar. So we have that 3 bar times 7 bar equals 3 bar times 3 bar in this ring, but 7 bar does not equal 3 bar. That means that this ring does not satisfy the cancellation property for multiplication. And this sort of failure of a ring to behave in the nice ways that we want motivates a couple of definitions. So first we have definition 88. Let's let R be a ring. A zero divisor of R is a non-zero element A belonging to R such that there exists another non-zero element B belonging to R such that A times B equals 0. So a zero divisor is something that's not 0, such that you can multiply it by something else that's also not 0, but the result gives you 0 back. Now this is not something that we encounter often when working in the integers or the real numbers or many of the other fields that we're used to working with, but it turns out that that's because these rings don't contain zero divisors, and that makes them special, and that's what we're going to be moving towards. But before we start looking at rings defined using zero divisors, let's see some examples of zero divisors in rings that we're already familiar with. So we can look at the same ring that we looked at in the previous example. In the ring R, which is Z mod 12Z, we have that 3 bar is a zero divisor, since 3 bar times 4 bar is equal to 12 bar, which is 0 bar, which is the 0 element of this ring. Now, importantly, you'll notice that neither 3 bar nor 4 bar are 0 in this ring. Nevertheless, their product gives you 0, and that's what makes 3 a zero divisor. Now, this also makes 4 a zero divisor, and in fact, zero divisors usually come in pairs. If you want to show that something's a zero divisor, you have to show that you can multiply it by something else to get 0, and then both of those things that you've got are zero divisors as long as neither one of them is 0 to begin with. This is one of our first examples. We could take a slightly more complex example. Let's let R be the set of 2 by 2 matrices with real entries, with matrix addition and matrix multiplication as their operations. This is a ring. And let's note that if we take the element 2, -3, -4, 6, and multiply it by 3, 2, 3, 2, this winds up giving us 0, 0. Sorry about that. I copied this down wrong. We want 3, 3, 2, 2. And that gives us, when we multiply these two matrices, gives us 0, 0, 0, 0, which is in fact the 0 element, the additive identity of this ring R. So that means that the elements 2, -3, -4, 6, and 3, 3, 2, 2 are 0 divisors in R. Now for a sort of non-example, let's let R be the ring Z adjoin X, that is polynomials in the variable X with coefficients in Z, integer coefficients. And let's let F be just the polynomial X contained in R. Now we claim F is not a 0 divisor. Now, as is typical when working with algebraic objects, proving that something doesn't have a property typically takes more work than proving that something does have a property. If we want to show that 3 bar is a 0 divisor, or that the matrix, one of the matrices that we had before is a 0 divisor, all we need to do is find one other non-zero element in the ring that you can multiply it by it to get 0. However, when you want to show that an element is not a 0 divisor, as in this third example, we need to show that no matter what non-zero element we multiply by F, we're not going to get the 0 element back. So no matter what we multiply F by, we're not going to get 0. So the way that we'll typically do that is to take some other random element of R, but we want it to not be 0, and we're going to try to show that F times G is not equal to the 0 polynomial. So that means that G is equal to a polynomial, a0 plus a1x plus ... plus anx to the n for some n that's at least 0, and importantly, with an not being 0. We can always choose for n here to be the degree of G, and because we've specified that G is not allowed to be 0, the leading coefficient of G cannot be 0. The only polynomial with a leading coefficient of 0 is the 0 polynomial itself. So now we have that F times G is equal to X times G, because F was just equal to X, which gives us a0x plus a1x squared plus etc., up to an x to the n plus 1. Now, since an is not equal to 0, that means that this polynomial fg is not equal to 0. So what we've shown is that no matter what g we choose other than 0 in the ring, if we multiply it by f, we can't possibly get 0. So that means that f is a non-zero divisor. Which means a non-zero element which isn't a zero divisor. So here we've shown that f is not a zero divisor, and it's also not 0, and so we call it a non-zero divisor. So a quick point of terminology here. So every element of a ring R is either a zero divisor, a non-zero divisor, or 0. And every element of a ring falls into exactly one of these categories. So these are an exhaustive and mutually exclusive list. So if something's a zero divisor, that means that A is not equal to 0, B is not equal to 0, but A times B is equal to 0. In this case, both A and B are zero divisors. A non-zero divisor means not a zero divisor and not 0, which means that A times B is not equal to 0 if B is not equal to 0, where A here is the non-zero divisor. And then, of course, we've got the element 0, which doesn't fall into either of these categories. We will often talk about zero divisors and non-zero divisors when discussing the elements of a ring, because they are very important for things like talking about the cancellation property. Now, if we adjust the argument that we just made to show that the element f in the polynomial ring with integer coefficients show that that's not a zero divisor, by a similar argument, we can in fact show that any element of that ring other than 0 is a non-zero divisor, or in other words, that the ring doesn't contain any zero divisors. Such rings are very useful to us, and we are going to give a name to rings that have that property in addition to one other property. So definition 89, a ring R is called a domain if it is a commutative ring with identity and has no zero divisors. So a ring R that is a domain if it's a commutative ring with identity and has no zero divisors. This term is sometimes called an integral domain. Some people use the term integral domain rather than simply domain, and the reason for that is because these are some of the most important properties that the integers have, the ring of integers has. And so an integral domain is supposed to be a ring that behaves like the integers. One of the most important properties of domains is the following. If you've got two elements that belong to a ring R, and if that ring is a domain, then we have the following property. If A times B is equal to 0, then A is equal to 0 or B is equal to 0. This is a property that we use in elementary algebra all the time. In fact, the strategy of solving a polynomial equation by factoring the polynomial and setting each of the factors equals to 0 relies on the fact that in the integers, if two things, or really multiple things, multiply together to equal 0, then one of the factors had to be 0 to begin with. And that comes from the fact that the integers are a domain. So this is one of the most important properties of a domain, but we'll see that there are several others. Domains have lots of very useful properties. Now, while the focus of calling a ring a domain is usually on the fact that it has no zero divisors. Don't forget that it also carries the information of being a commutative ring with identity. So if any ring is ever referred to as a domain, not only does it have no zero divisors, but it's also a commutative ring with identity. So you can use any of those facts as well when working with the ring. Let's see some examples. The following rings are domains. So we've got, well, the integers, of course, that's what the whole property is sort of modeled on. But we know that the same also holds in the rationals, the reals, the complex numbers. We know that in any of these cases, if two numbers multiply to equal 0, then one of the two numbers that we started with have to be 0. Similarly, if we take the set of polynomials with coefficients in any one of these rings, then these are all domains also. We're going to be talking more about polynomial rings in particular in a later lecture, and we'll see that many properties of the coefficient ring carry over to the polynomial ring. In particular, the property of being a domain carries over. So if the ring is a domain, then the polynomial ring with coefficients in that ring is also a domain. One that shows up a lot in number theory and other various places is the ring Z adjoin square root of n. Now this is defined to be the set of numbers a plus b times the square root of n, where a and b belong to Z, where n is a non-square integer. Now, these rings are not ones that we've looked at a whole lot yet, but we'll come back to and talk about at a later date. The multiplication of elements in this ring works by distribution. So, for instance, if we take, let's suppose n is 5, and we take a couple of elements here. If we take 3 plus 2 square root of 5 times 1 minus 4 times the square root of 5, then we distribute things. 3 times 1 is 3. 3 times negative 4 square root of 5 is negative 12 square root of 5, plus 2 square root of 5 times 1 is 2 square root of 5. And then 2 square root of 5 minus 4 square times negative 4 square root of 5 is negative 8 times 5. So we wind up with 3 minus 40 is negative 37, and negative 12 plus 2 is negative 10 square root of 5. And so in particular, we can see that we started with two elements of this ring Z adjoin the square root of 5, and the result is another element of Z adjoin the square root of 5. Now the point is that if n is not a square integer, this ring is also a domain. Now to check these things, now notice that you have to show that it's a commutative ring with identity, and then show that if some element is non-zero, or if you multiply two non-zero elements together, you won't get 0. Or equivalently, show the fact from elementary algebra that if two of these elements do multiply together and equal 0, then one of those elements had to be 0 to begin with. Now, very importantly, we also have the rings Z mod PZ. Now, we know that this doesn't hold for all of them. We've already seen that Z mod 12Z is not a domain because we saw that 3 bar times 4 bar is equal to 0 in that case. But if P is a prime number, these rings are domains. So of all the rings Z mod NZ, some of them are domains and some of them are not. The ones that are domains are the ones where we are modding out by a prime number, and where our operations are addition and multiplication modulo a prime number. Now, on the other hand, the following rings are not domains. We have the set of matrices, n by n matrices over R, so long as n is greater than or equal to 2. We saw an example of this where n was 2 earlier. Z mod nz, where n is not a prime number. So of all the rings Z mod nz, you can know precisely whether that ring is a domain or not by checking to see whether you're modding out by a prime number or by a non-prime number. We could also take the direct sum of Z and Z. Now, we haven't looked at this in detail yet, but this follows a construction very similarly to the construction of a direct sum of groups. And this is, by definition, the set consisting of all pairs A and B, where A comes from Z, B comes from Z, and then the addition of elements here is just component-wise addition, and the multiplication is component-wise multiplication. And the point is that Z direct sum Z is not a domain. This is perhaps a little bit surprising, since Z itself is definitely a domain. But in fact, if I have any two non-trivial rings and I take their direct sum, using exactly the same formulation as we did in part 3 here, that resulting ring will not be a domain, no matter what. We'll see some of this. You'll see some of this in your exercises, that direct sums of rings do remember some of the information, some of the properties from the rings that make them up, such as having identity, being commutative, things like this, but they definitely don't remember the property of being a domain. You lose domainness pretty much immediately whenever you take direct sums of rings. All right, so now let's see that working in domains exactly gives us the cancellation property that we like, that we know from working with groups and would like to continue to use. So let's look at Theorem 90, which we can call cancellation in domains. It says if the ring R is a domain and A, B, and C belong to R, and A times B equals A times C, then B equals C. So this tells us that while A may not have an inverse, A may not be a unit in the ring R, as long as the ring R is a domain, then we can at least say that we can cancel them. I should we definitely require that a not be 0 here, because if a is 0, of course, then 0 times b equals 0 times c for any b and c, so this doesn't make sense for non-zero a's, but it does make sense, or it does make sense for a's that are equal to 0, but it does make sense for any a that's not 0. So let's see the proof. And the proof of this is a pretty simple example about how we can use the properties of rings to really manipulate equations in ways that are somewhat familiar to us from elementary algebra, but that work in the more abstract setting. All right, so let's suppose R is a domain. A, B, C belong to R. A is not equal to 0, and AB is equal to AC. Well, then we can subtract the element AC from both sides to get that AB minus AC equals 0. And as I mentioned in the last lecture, you should always be on the lookout for where you're going to use distribution, because especially for the sort of elementary proofs that we've got going on, we're going to be using distribution in almost every proof. In this case, we're going to use it to factor the a out on the left. By distribution, this means that a times b minus c is equal to 0. Therefore, a equals 0 or b minus c equals 0 since R is a domain. Being a domain means that if two elements of your ring multiply together to equal 0, then one of them had to be 0 to begin with. So if a times b minus c equals 0, then a equals 0 or b minus c equals 0. But one of our hypotheses was that a is not equal to 0. So since a is not equal to 0, we have that b minus c equals 0, and so bringing c to the other side, we get that b equals c, or if you like, adding c to both sides. So that finishes the proof here. We have that if AB equals AC and A is non-zero, then B equals C. Now this only applies in a domain, but many of the rings that we care about, that we deal with, often are domains, and so we're going to take advantage of this theorem reasonably often. All right, so the next thing we want to do is look at the relationship between domains, which are a special kind of ring, and fields, which are also a special kind of ring, which we defined. And it turns out that fields are a subset of domains, or in other words, we have Theorem 91, which says that if F is a field, then F is a domain. Let's prove this. Let's let F be a field. By definition, F is commutative with identity. That was part of the definition of being a field. So we got that F is commutative with identity, and so the only thing we have left to prove in order to show that F is a domain is that it contains no zero divisors. So let's suppose that A times B equals 0, and A is not equal to 0. So let's suppose we have the element A, B, the product A times B equals 0, and A is not equal to 0. I should say, suppose A and B belong to F with this property. Now, since A is not equal to 0 and F is a field, A has an inverse. A inverse, a multiplicative inverse. So multiplying both sides by A inverse, we get that A inverse AB equals A inverse 0. So A inverse times A is just the element 1. We know that anything times 0 is 0. We proved that last time. And we know that 1 times B is equal to B. So that means that B is equal to 0. So what we found is that if A is not equal to 0, then B is equal to 0. So that means that A is not a 0 divisor of F. And since this applied to any A, any non-zero A, this means that F is a domain. So every field is a domain, but not every domain is a field. Most of the examples that we saw earlier of domains were not fields. In particular, the set of integers is not a field. And so that's an example of a domain. That's not a field. However, it turns out that some domains are fields, and certain types of domains can be shown to be fields fairly quickly. Let's look at Theorem 92. If R is a finite domain, then R is a field. So here, finite means having only finitely many elements. So if R is a ring, it's a domain, so it's commutative with unity, contains no 0 divisors, and has only finitely many elements, then it has to be a field. This is perhaps surprising because we've seen, as we just mentioned, a lot of domains that aren't fields. Being a field is a very strong property. It requires a lot. It requires every element to have a multiplicative inverse. And being a domain is much, much weaker than that. There are lots and lots of domains that aren't fields, but if you ever have a domain that's not a field, that ring has to have infinitely many elements, according to Theorem 92. This is perhaps a little surprising, but let's see why this is the case. So let's let R be a finite domain, and let's let A be an element of R, which is not 0. We want to show that R is a field, which means we need to show that it's a commutative ring with identity and that every non-zero element has an inverse. Well, we already know that R is a commutative ring with identity because we know R is a domain. That's part of what we've assumed. So what we really need to show is that A has a multiplicative identity. So we want to show that A has a multiplicative identity. Well, first of all, notice that if A is equal to 1, if it is the not multiplicative identity, multiplicative inverse. We've already assumed that there exists an identity. We want to show that A has a multiplicative inverse. Now, first of all, if A is equal to 1, then A times A is equal to 1 times 1 is equal to 1. So A is its own inverse. That handles a simple case. So let's assume that A is not equal to 1. Let's assume A is not the multiplicative identity and show that it has a multiplicative inverse. Now, let's consider the sequence. A squared, A cubed, A to the 4th, A to the 5th, etc. Let's just take A and keep raising it to higher and higher and higher and higher and higher and higher powers. Well, because R is finite, this sequence must repeat. Or not that the sequence must repeat its order. This sequence must have two elements, A to the I and A to the J, with I less than J and A to the I equals A to the J. Basically, there's not enough room in the ring. This sequence, A squared, A cubed, etc., is an infinite sequence, and each one of these powers hits some element of the ring R. Eventually, you're going to run out of elements of the ring R, and two powers of A are going to land on the same point. Now, you can, of course, go further and say that there's some element of R that is equal to infinitely many different powers of A, but we just need one of them. We need that I is less than J and A to the I is equal to A to the J. Now, we can use cancellation. So that means that A to the I equals A to the I times A to the J minus I. That's just normal power arithmetic. So by cancellation, 1 is equal to A to the J minus I. So what we've done here is we've canceled the A to the I's on the two sides of the equation. We could treat the left-hand side, of course, as being A to the I times 1, and we can cancel both the A to the I's. Normally, we'd have to be careful about whether this A to the I is multiplying on the left or on the right, but because we're in a domain, everything's commutative, so we don't have to worry about that. So we get that A to the J minus I is equal to 1. Now, since A is not equal to 1, we have that J minus I has to be greater than or equal to 2. We know that J is greater than I, but if J minus I were equal to 1, then that would mean that A to the first power is equal to the multiplicative identity, and we've already assumed that A is not equal to the multiplicative identity. So that means that J minus I has to be greater than or equal to 2, and therefore we can write that the multiplicative identity 1 is equal to A times A to the J minus I minus 1. And this still makes sense because since J minus I is at least 2, J minus I minus 1 is still at least 1. But look at what we've done now. We've expressed the multiplicative identity as a product of A, the element that we cared about, with something else. So this means that A to the J minus I minus 1 is a multiplicative inverse of A, hence the multiplicative inverse of A. And so A is a unit. Now, notice that we have now shown that every element other than the multiplicative identity is a unit. And that's not 0. Also, we have that the multiplicative identity itself is a unit because it always is. And so we have that all elements of the ring other than 0 are units. Therefore, R is a field. Okay, so if we have any finite domains, then they have to be fields. This can be combined with our previous observation about the rings Z mod PZ with P a field to note that the ring Z mod PZ is a field for every prime number P. Now, these are often referred to as the fields FP. We'll sometimes see the notation FP, and it means the field Z mod PZ. So this is a field with P elements. What we will find eventually when we start talking about fields in earnest is that this is the only field with P elements up to isomorphism. We're going to talk about ring and field isomorphism in a little bit. And so we often use this notation or describe this notation as the field with P elements, because up to isomorphism there's only one, and it's this Z, and it's Z mod PZ. We don't define this notation for numbers that aren't prime numbers, so there is no F4 or F6. Okay, so a little bit of notation. This is similar notation to what we've used for groups, and we've already sort of been using it a little bit in the guise of powers, but we want to make it explicit here. So let's let R be a ring and X an element of R. Now, if N is a positive integer, then nx is defined to be the n-fold sum of x. That is the thing that we get when we add up n copies of the element x together. If n is a negative integer, then nx is equal to negative x minus blah, 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 minus x, where here in this case we have negative n copies. If n is a negative integer, then of course negative n is a positive integer. So we will we'll use this notation. We'll talk about these sorts of expressions even in cases where the elements of our ring are not numbers. We will use this notation in order to describe the n-fold sum of some numbers of copies of an element, or the additive inverse of that element. It turns out that we can show that if I have mn times xy, where m and n are any integers and x and y are any ring elements, that's the same as mx times ny. So there's a sort of associativity thing going on here, where it really doesn't matter where you attach the multiples to in a situation like this, because this is also equal to nx times my. All right. Now let's use this notation to note something important about the rings Z mod PZ. So note, for any element x in z mod pz. First of all, we can write it as x bar so that it matches the notation that we typically use here. We have that p times x bar, where p is the prime number here, is equal to, by definition, x bar plus x bar, blah, 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 plus x bar, where we've got p copies of x. And we add things up, modulo p, by adding them up first and then taking their equivalence class, modulo p. And then this is, this turns out to be the equivalence class of the number px. And so when using the notation that we just had, then the notation outside for just this integer describing the n-fold sum can actually be pulled inside the notation here. However, you'll notice that this element px here is equal to 0. And that's because since px minus is equivalent to 0 mod p, remember that two things are equivalent modulo p if their difference is divisible by p. Well, in this case, their difference is just the number px, and the number px is certainly divisible by p. But what this means is that no matter what number you choose, no matter what element of z mod pz you choose, if you add up p of them, you get 0 back. No matter what. And in fact, none of this is actually special about p. Notice we didn't use the primeness of what was going on here. Everything works perfectly well if we just take any positive integer n here. So we run into this situation where if we've got some number n, where if you add up anything in the ring that many times, you get back to 0. This is something that occurs, well, it occurs in every finite ring, and it occurs in many other kinds of rings as well. So we give it a name. Definition 93. Let's let R be a ring if there is a positive integer n such that nx equals 0 for all x in R, then the smallest such n is called the characteristic of R. And if no such integer exists, the characteristic of R is 0. Now, this can seem a little strange. Why would we call it 0? We'll see in a few more lectures why this makes sense. It can also make some sense to describe the characteristic as being infinite in such a case, but the definition of characteristic has it this way. So if we have a ring R such that if you add up anything, it eventually comes back around to 0, and there's some some number n such that that always happens, then we refer to that as the characteristic of R. Incidentally, this is possibly one of the reasons why rings carry the name rings. Let's look back at our friend Z mod 12Z. And what I want to do actually is think of this ring as sort of being like arithmetic on a clock face. Now I'm going to start at 0 up here. And we can think of the elements of Z mod 12Z as lying on a clock face here. And so, for instance, if I take 7 plus 6, well, we know that's 13 bar, which is equivalent to 1 bar. And we could also think of this as being like starting at 7 and then moving 6 units around the circle and seeing where we end up. Or in other words, someone says, it's 7 o'clock now, what time will it be in 6 hours? The answer is 1 o'clock, because you've gone around the circle. Furthermore, we can see that this ring has some positive characteristic. No matter what number you choose here, no matter what element of the ring you choose here, if you go around the circle enough times, eventually you're going to come back to 0. Let's see. Let's convince ourselves of that. If you keep adding it up over and over again. So let's take 5. If we start here at 5, and we keep adding up 5 repeatedly, we get 5. 5 plus 5 is 10. 10 plus 5 is 3. 3 plus 5 is 8. 8 plus 5 is 1. 1 plus 5 is 6. 6 plus 5 is 11. 11 plus 5 is 4. 4 plus 5 is 9. 9 plus 5 is 2. 2 plus 5 is 7. And 7 plus 5 comes back to 0. So you can see, even though it bounced around a bunch of times, eventually it got back to 0 as it wound its way around the circle. And indeed, it took exactly 12 times to get back to 0. And so we can note that the same sorts of things happen with every element of this ring. Now, some elements will arrive at 0 faster. So, for instance, if I start with 8 and try to figure out, all right, well, what's the minimum multiple of 8 that gets me back to 0? Start with 8, and 8 plus 8 is 16, which gets us back to 4. And then 4 plus 8 is 12, which gets us back here to 0. So we can see here that 12 times 5 bar equals 0. 3 times 8 bar equals 0. And in fact, we can do this for all of them, and we can see that the smallest, or rather that every number here comes back to 0 bar in at most 12 steps. This means that 12 is the characteristic of this ring because it's the smallest number such that n times x equals 0 for all x's. This is the smallest number that works for all of them. So this means that the characteristic of Z mod 12Z is 12. So we can see some more examples. Actually, sorry, rather than moving to the examples, let me move to the theorem that lets us calculate the characteristic of a ring easily when that ring has identity, which most of the rings that we examine will have. So let's let R be a ring with identity. The identity element has infinite order in the group R plus, R with addition, if and only if the characteristic of R is 0. When the order of 1 in the group R plus is finite, it is equal to the order of, I'm sorry, to the, not to the order, to the characteristic of R. All right, so let's see a proof of this. So first of all, if 1 has infinite order in the group R with addition, then n times 1, which is 1 plus 1 plus plus 1, n times, that's not equal to 0 for any n. And because that's what it means to have infinite order in the group, it means that no matter how many times you add it to himself, you'd never get back to the identity of the group. And the identity of the group R plus is 0. Because n times 1 never equals 0, that means that there can't be any number that multiplies by everything in the ring to give 0. And so that means that the characteristic of R is 0, because there's no element that multiplies 1 to give you 0. And so there can't be anything that multiplies everything into 0. So now, suppose the order of 1 is n, which is a finite number in the group R plus. So what we want to show now is that if I take n times any other element of the ring R, then we will get 0 out of it. So now, for any x in R, we have that n times x, well, it's certainly equal to n times 1x, because x is equal to 1 times x. 1 is the identity. But this is equal to n times 1 times x. Here, this 1 here is still a ring element. This is still an element of the ring R. But we were told that the order of 1 in the group R plus is n, which means that if I take n times 1, that's 1 plus 1 up n times, and we assumed that that was 0. So that's 0 times x, which is 0. So what we have is that if some element multiplies 1, or some integer multiplies by the multiplicative identity to give you 0, then it will multiply any number in your ring to give you 0. So let's use this to calculate some examples. Let's let R be z mod 8z adjoin x. So these are polynomials whose coefficients are elements of the ring z mod 8z. So now R is a ring with identity 1 bar. Now this is the constant polynomial 1. And now we have that 1 times 1 bar is not equal to 0 bar. 2 times 1 bar is not equal to 0 bar. All the way down, 7 times 1 bar is not equal to 0 bar. But we have that 8 times 1 bar would be 1 bar plus 1 bar added up 8 times. That is 8 bar, which is equal to 0 bar. So that means that the order of 1 bar in the ring R, or in the group rather, the group R with addition, is 8. So that means that the characteristic of R is 8. There are lots of things that we can do in rings with positive characteristic versus rings of characteristic 0. And every ring has either positive characteristic, some number, or characteristic 0. Of special interest are those rings which have positive characteristic, which is a prime number. Those are even more interesting. There's much more you can do with that, a lot of theory that you can develop, which we may be able to get to later in this semester. All right, so the last thing that we want to see is that when the ring R is a domain, including when it's a field, then the characteristic can't be too many things. Theorem 95 states that let R be a domain. The characteristic of R is either 0, it could be 0, or a prime number. In particular, it can't be a non-prime number. It can't be a composite number, and it can't be 1. Let's see this. Let's suppose that, let's suppose the opposite. Let's suppose that the characteristic of R is a composite number. RS, where R and S are both integers, and they're both greater than 1. So whatever the characteristic is, we assume it's a composite number, so it can be written as a product of 2 other numbers that are at least 2. So now we have that 0 is equal to RS times 1. That's just the definition, part of the definition of what it means to be the characteristic. Now, using the properties that we had before, we have that RS times 1 is equal to RS times 1 times 1, because 1 times 1 is equal to 1. But it turns out that we can group these around basically however we want. And if I have RS times 1 times RS times 1 times 1, that's the same as R times 1 times S times 1. So we have that the two numbers R times 1, or the two ring elements rather, and S times 1 multiply to equal 0. Since R is a domain, R times 1 equals 0, or S times 1 equals 0. But this is a contradiction. Since R is less than RS and S is less than RS. So both of these numbers are less than the characteristic of 1, or of the ring R, which is the same as the order of the element 1 in the group of the ring with addition. And so we arrive at a contradiction here. So the characteristic of R has to be either 0 or a prime number. Now, the eagle-eyed among you will notice that I have technically left out the case of what happens if the characteristic is 1, but one can easily show that the characteristic of the characteristic of a ring can only be 1 if that ring is the trivial ring. It is the ring containing only one element. If you're a domain, then that means that you are a ring with identity, which means you're non-trivial. So technically, a little bit of argument should be done in there for why the characteristic can't be 1, but the characteristic can never be 1 for any non-trivial ring. So we'll basically never run into that situation.